second, quantization and its application in quantum optics. So what's this talk about? First, we will introduce bosonic second quantization in the Wolfram quantum framework. Then we will talk about atom field interactions, describing the Jaynes Cummings Hamiltonian and observing Rabi oscillations. Then we will talk about decoherence and dissipation interactions. We will observe the evolution of the states in dissipative environments, and we will solve master equations in quantum optics. To start, we have to load our favorite paclet, quantum framework, where we install it. We load the framework along the second quantization, that is a set of functionalities built on top of the quantum framework. Here we have a collection of states and operators that are commonly used in quantum optics. So how does this work? Of course, we cannot work in an infinite dimensional space. We have to truncate the space to favor the discrete computation capabilities of the quantum framework. Especially, we will make use in full power the qubits feature. Our fundamental object is the annihilation and the creation operator. Of course, one is just the Hermitian conjugate of the other. By default, we have a truncation size of 16, such that we can call all our definitions without passing an explicit size. But it's possible to change the default truncation size using the function set Fock space size. In this case, we pass it a parameter 20. Or we can also specify a desired size for a particular calculations. For example, here we use the displacement operator with that size of 21. Let's see some simple case examples. Let's start for a trivial example, just applying the annihilation operator applied to the vacuum. Of course, that returns a scalar 0. We can also see the photon distribution of a coherent state. Here we try with alpha equals to 1 plus 2i. We can also work in a two-mode Hilbert space, considering the quantum tensor product of the Fock state 2 and Fock state 5. And we use Ben to just apply the annihilation operator to each particular space of the respective modes. We also have ways to calculate the mean number of photons of a state by 3 different ways. We can use quantum measurement operator using the number operator. We can use bracket notation in this manner, or we can also use the probabilities associated to the density matrix, especially the diagonal. We also have quasi-probability representations or phase space distributions. What this Wigner and Husimi Q representation does, they calculate the standard phase space functions, but in a grid of phase space points. With this, we can get these plots about the Wigner and Husimi for the Fock state number equals to 5. That representation can be interpolated in a continuous function. We can integrate it over all phase space, or we can calculate an average, for example, the x squared operator. Now let's talk about atom field interactions. We will briefly start with the semi-classical approach, considering two levels with energies EA and EB, such that EA equals to 0, and we let the Bohr frequency equals to EB, the difference of energies divided by h bar. The full Hamiltonian takes this form that is time-dependent. We can define the atom basis, the Hamiltonian, and we consider an initial state that is general. We consider these time-dependent coefficients. And to solve it, we manipulate the Schrödinger equation. We use some symbolic manipulation and replacement to make it in a simple form, discarding the fast oscillating terms. Having that equation, we can just solve it for the time-dependent coefficients, and we can encode it in a quantum state with parameters. We can plot the probability of finding the atom in the excited state, having it initially in the ground state, something that's called the transition probability. We do it for different detonings, and we can see this nice plot of the Rabi oscillations, which coincide with a textbook example from the Greenberg book, which is nice. But now we can go to the full quantum model, the Jaynes-Cummings Hamiltonian. We quantize the field and we can quantize the atom. We define the sec Fock space size relevant to the simulation. We define the sigma operators. We define our free Hamiltonian, the atom field interaction term, and we go to the interaction picture. So we evolve our interaction term by the free Hamiltonian. And this interaction Hamiltonian, if we consider exactly resonance, is independent of time. So we can just evolve it with a unitary operator. Having this unitary operator, we can evolve different states. For example, let's consider an initial state such that the atom is in the ground state and the field is in a Fock state 1. We define the state, we apply the operator, we get this resulting state as a function of time. We see this is coupled the levels G1 and E0. So there's an exchange of energy between those states. We define the probability of finding the atom in the excited state. And we plot it as a function of time, and we get these nice gravity oscillations that go from 0 to 1, coinciding exactly to the semi-classical case. But now let's consider a more interesting initial field, such that it's in a coherent state. And in this case, we will see more interesting results. We define the state, we evolve it, and we define this CET, CGT, that are coefficients related to the probability of finding the atom in the excited state and in the ground state. With that, we can calculate the population inversion. And if we plot it as a function of time, we get this fascinating result that is only present in the quantum regime. Instead of getting pure gravity oscillations, we get collapse and revivals. We also compare with a result of a textbook where we can verify this really nice result. We also plot the evolution of the photon number distribution profile. We see this some crazy oscillation, but we see the initial state is this Poisson distribution. But if we consider the time around the revival, we get something that looks a bit more organized. But of course, we never recover the initial state. It's just at the revival, we get something that's more organized. Now, the case when the field is in a thermal state, we consider the atom initially in a superposition of excited and ground state, and the field in a thermal state such that the mean number of photons is equal to 5. In this case, we are working with a density matrix, so the evolution is of this equation. We have this rho t, and after we trace out the field component, we just have an atom matrix that's related to the atom. We can plot the EE and the EG components of this matrix. We see that we get oscillation for the EE term, and for the EG that is off diagonal, we get it starts to decrease to 0 and it will oscillate around this. But we know that the atom should get thermalized, so that means that the time average of the coherence should go to 0. We can verify that plotting the time average of that matrix component. And we can see that if we wait a sufficiently long time, that time average is essentially 0. Now let's move on to the other big topic, that is dissipation, decoherence, and master equations. Let's start with a case of a decay of a coherent state. We define the relevant definitions. The initial state is a coherent state. We consider this quantum operator Hamiltonian. So we pass just the regular number operator for the Hamiltonian. We consider Lindblad jump operator a single photon loss. We have in this case, we're just evolving with exponential because this is time independent. As a function of time, we say that the quantum similarity to this analytical expression, and we also say the mean number of photons. We know that with photon loss mechanism, this state will remain coherent. That is important, but the amplitude will behave in this manner. There is an exponential decay factor and just a phase oscillating term. So essentially, the mean number of photons decay. If we plot the quantities we just described, we get this nice decay for the mean number of photons. And the quantum similarity, as expected, will behave like the analytical expression. The fidelity is around 1. But having this behavior of the complex amplitude, we can get a nice visualization of this, because the complex amplitude will rotate and will also approach the origin because of this exponential decay factor. So we can show this evolution of the Wigner representation. We can see it has the same shape because it remains coherent, but it will spiral towards the origin. We can also try a different case, that is generation of coherent states from decoherence, something that is called optical balance. So we're considering a driving field in this case that is related to this parameter G. So we use the quantum operator, the Hamiltonian. We consider the drive. So the idea is that this driving field will balance out with the single photon loss. We use a random pure initial state. So we know the steady state solution should be a coherent state of this analytical expression. We evolve using quantum evolve, but now we use numerical. We go from 0 to 3. We have the quantum state. We compute the fidelities. And we see that it will eventually converge toward this coherent state. And this will work for any initial condition. This is a steady state solution. If we consider, instead of a random pure state, we consider the ground state, the evolution will be of this form, but only for short times, where the complex amplitude is independent of the damping parameter. We save exactly the same quantities as before, and we plot it. So this is the optical balance for short times. We see that the fidelity is around 1 until the approximation is no longer valid. But of course, the mean number of photons is always increasing because of this T will be the amplitude is increasing as a function of time. Now let's talk about Kerr interaction. This is a really interesting topic, and we will explore it with a 2-photon drive Kerr nonlinear resonator in a frame rotating at a resonator frequency to prepare and stabilize states in a manifold of coherent states. This is interesting, for example, in quantum computing for cat qubits, where a 2-level system is encoded in a manifold of coherent states. We see that we define here the Hamiltonian. The K is the Kerr nonlinear constant, and this the driving amplitude, and we are considering as a jump Lindblad operator, just the annihilation operator. So it does mean single photon loss. We take these parameters based on this paper of Puri. We use the ground state as an initial state. We define the Hamiltonian, the evolution, using these Lindblad jump operators. And we know the steady state solution is this mixture of coherent states. So after the evolution, at the final time, we compute the fidelity, and we get of 96%. Of course, because there is photon loss, it will not be 100%. We can also, we can see this evolution in animation. It starts in a ground state, and it converges to 2 coherent states. So this means that the ground state is transformed to the manifold of coherent states. Other case is the adiabatic initialization of a cat state. So instead of using a constant drive, we are not using a time-dependent drive, where this tau parameter is called the adiabatic parameter that will determine the adiabatic evolution. It's exactly the same Hamiltonian, but now we are making use of an important theoretical fact that the ground state will evolve to an even cat state, and that Fock state 1 will evolve to an odd cat state, because they are 2 degenerate eigenstates of the Kerr nonlinear resonator without driving. We find the Hamiltonian, we evolve it using numerical from time 0 to 2, This alpha t is just a way of defining the complex amplitude of the cut states as a function of time. We compute the fidelities respect to the cut state exactly to the evolution. We get 99%. We get a really nice result because for this simulation, we're considering no photon loss. But if we use photon loss, it will get lower, probably around 95%. Here is the Wigner representation of this adiabatic evolution. We see it will go to a well-defined cut state around time equals 0.5, 1.5. As a final topic, we will explore Jaynes Cummings, but now with dissipation. We consider exactly the same Hamiltonian as before, but in the master equation, we include this jam operator now related only to the decay of the atom and only to the single photon loss. If we consider an initial state E, that means excited state, and for the field, a Fock state equal to 2. We could define some constants for the simulation, but they were just completely arbitrary, just for the sake of the time window that I am using. It can perfectly be changed. We will define all the relevant operators, the Hamiltonian, the jump operators, the initial state, and we move on to the results. We are supposed to see damped gravity oscillation in this case. We use this atom probability to record the probability of finding the atom in the excited state for these different times. We do the simulation for 3 damping constants, 0.8, 0.4, and 0.2. Of course, when the damping constant is higher, we get more damped gravity oscillations. So we get the result that is expected. But we can also fix the damping constant and evolve different states. Here I am using for 0.8. This is the oscillations, damped gravity oscillation for the vacuum. This is for the Fock state equal to 1, and this is for 2 coherent states. For the coherent states, we see that there is not any more collapse and revivals. We get like some kind of oscillation, but it will like damp out over time. Of course, we are just using some numerical constants, but you can explore all different type of dynamics and evolutions just playing with the parameters. So this is a rich system. So to summarize, we have an implementation of the second quantization that was integrated in the quantum framework. And we clearly showcase versatility of the quantum phenomena that can be simulated. This tool can also be useful to develop educational content for courses in introductory quantum optics and quantum mechanics. And we see that our Hamiltonian and Liouvillean definitions can be quite useful in research-oriented simulations that require problems that can be modeled with master equations. Thank you, and that is everything. And this is the reference.